Importance of Scattering of Light by B.N. Achar. Sun produces white light. White light is made up of 7 colors. They are violet, indigo, blue, green, yellow, orange and red, briefly known as VIBGYOR. Light can be scattered and redirected in many directions. The nature of scattered light depends on the surface of the material, size of the material and wavelength of the light. Scattering may be elastic or inelastic. Types of scattering. There are 4 types of scattering. They are Tyndall scattering, Rayleigh scattering, Mie scattering and Raman scattering. John Tyndall from Laglin Bridge, County Carlow, Ireland, studied the scattering of light by colloidal particles. Light scattering by particles in a colloidal solution or particles in a fine suspension is called Tyndall scattering or Tyndall effect. Examples for Tyndall effect. Visibility of the headlight beams of the vehicles in fog. In everyday life, seeing the bluish hue of smoke coming from vehicles' engines. Appearance of blue hue of milk. Visibility of sunlight rays coming through a window. Scattering of light in forests. Tyndall effect is the scattering of light by colloidal particles. Colloid can be defined as a type of homogeneous mixture in which the dispersed particles do not settle out. Examples: buttermilk, smoke, fog, ink, paint, etc. The important things to be remembered here are: a scattering material must have one or more of its dimension, either length, width or thickness, in the approximate range of 1 to 1000 nanometer. Tyndall effect is similar to Mie scattering without the restriction to spherical geometry of the particles. It is particularly applicable to colloidal mixtures and suspensions. The Tyndall effect is caused by irregular reflection of light by very small particles in suspension in a transparent medium. A typical colloidal particle has diameter around 0.0022 to 0.2 millimeter, which is normally bigger than the particles found in a solution and smaller than particles in suspension. 2 conditions are to be satisfied to observe Tyndall effect. They are: firstly, the diameter of the dispersed particles should be smaller than the wavelength of light used. Secondly, refractive indices of the medium and the colloidal particles must be different in magnitude to a large scale. Applications of Tyndall effect are many. A few applications are mentioned here. To determine whether a mixture is a true solution or a colloid. Commercially used to determine the size and density of particles in aerosol as well as other colloidal matters. Water pollution level in wastewater treatment. Studying the medicines in colloidal form. In the study of sewage disposal. Purification of water. Pulp and paper industry uses Tyndall effect to monitor the clarity of the mild acids used in the production of paper. This effect is applied in the study of smoke, precipitation, etc. Lord Rayleigh from Langford Grove, Essex, England, showed in the year 1871 that the amount of light scattered is inversely proportional to the 4th power of wavelength for sufficiently small particles. It follows that blue light is scattered more than red light by a factor of about 8.4. He was awarded Nobel Prize in Physics in the year 1904. A brief summary on the particle dimensions and scatterings is given here. The particles with dimensions greater than 10% of the wavelength of the incident radiations is called the large particle scattering. But when the particles with dimensions greater than 3 by 2 of the wavelength, the scattering phenomenon terminates. Scattering process with particles of dimensions greater than twice the wavelength results refraction or reflection. For particles with dimensions not greater than 5 to 10% of the wavelength, the scattering is known as Rayleigh scattering. Rayleigh scattering. When a beam of white light falls on a particle or molecule whose dimension is not greater than 5 to 10% of the wavelength of the incident radiation, light will be scattered symmetrically about the scattering center. The blue lines indicate the vector quantities of the scattered radiation. This type of scattering is known as the salient features of Rayleigh scattering are presented here. First one, Rayleigh scattering is elastic in nature. Second one, the particle dimension size is smaller than 5 to 10% of the wavelength of the electromagnetic radiation. Third one, Rayleigh scattering is relatively symmetrical around the scattering center of the particle. Fourth one, the intensity of the Rayleigh scattering is proportional to the inverse fourth power of the wavelength of the electromagnetic radiation. Fifth one, blue color of the sky at noon and red color of the sky at sunset as well as sunrise can be explained due to Rayleigh scattering. Sixth one, the intensity of the Rayleigh scattering is smaller than the Tyndall scattering because of the smaller size of the particles involved. Rayleigh scattering is responsible for the blue color of the sky. This can be understood by considering the plot obtained by plotting percentage of scattering of direct sunlight versus wavelength of the radiation. A figure as shown here will be obtained. This figure clearly indicates that shorter the wavelength of electromagnetic radiation, greater will be the intensity of scattering. In other words, as the wavelength of incident radiation increases, the percentage efficiency of scattering decreases. A beam of light with wavelength lambda falling on a particle whose dimension is not greater than 5 to 10% of the wavelength of incident radiation. Light will be scattered symmetrically as shown here in the case of Rayleigh scattering. The intensity of the scattered radiation can be determined by a detector kept at a distance r from the scattering center. Lord Rayleigh derived an expression for the intensity of scattered radiation as Is is equal to 8 pi to the power 4 alpha square into 1 plus cos square theta into I0 whole divided by wavelength to the power 4 r square, where alpha is the polarizability of the particle, lambda is the wavelength of incident light, I0 is the intensity of incident light, theta is the angle between the directions of incident and scattered lights, r is the distance from the center of the scattering and the detector, Is is the intensity of the scattered light. Or, being all other factors constant for a given condition, Is can be written as proportional to 1 by wavelength to the power 4. This means, for an example, Is corresponding to 400 nanometer will be about 7 times greater than the intensity of the scattered radiation corresponding to the wavelength 650 nanometer. Sky appears blue at noon, orange while sunrise and sunset. For example, sky at noon, sky at sunrise, sky at sunset. These can be explained due to the Rayleigh scattering. Why sky appears blue at noon, orange while sunrise and sunset? This can be understood by the following discussion. Earth has denser part of the atmosphere about 150 kilometers from the surface. Less Earth's atmosphere when we look overhead, and so blue light will be scattered more efficiently than the other colors. Hence, the sky appears blue at noon. More Earth's atmosphere at any horizon for sunrise and sunset than for noon. That is about 50 times greater Earth's atmosphere at any horizon than the atmosphere when we look overhead. We shall continue the discussion in the next slide. The sky appears orange while sunrise and sunset. For example, sky at sunrise, sky at sunset. In almost every location around the globe, the sky appears orange at sunrise and sunset. When we look towards any horizon, we are looking through more of Earth's atmosphere than when we look overhead. Sunlight passes through more air at sunrise and sunset than during the day. The atmospheric path is long enough to scatter all of the blue and violet lights out of the line of sight. Other colors continue on their way to the eyesight. Hence, sky appears orange while sunrise and sunset. Gustav Mie from Rostock, Mecklenburg-Schwerin, Germany, in the early 1900s discovered the scattering of light by spherical particles. Mie scattering, in broader sense, can be defined as scattering of light by spherical particles of any diameter. Mie scattering. For smaller particle size greater than 10% of the wavelength of incident light, light will be scattered with lesser symmetry than the Rayleigh scattering as shown. For larger particle size, the pattern of scattering will be similar to the smaller particle size, but the intensity of the scattered light in the forward direction of the incident radiation increasing with increasing the size of the particle. Mie type of scattering is responsible for the appearance of the clouds in white color. Size of the cloud droplets will be usually having a diameter of 20 micrometers or so. This is large enough to scatter all the visible wavelengths more or less equally, and all of the light which enters cloud will be scattered, and hence clouds appear white. When clouds become very big, lesser of the incoming solar radiation makes it through to the bottom of the cloud. This results darker appearance of the clouds at the bottom. The salient features regarding Mie scattering are given here. Mie scattering is caused by pollen, dust, smoke, water droplets and other particles in the lower portion of the atmosphere. Mie scattering in broader sense can be defined as scattering of light by spherical particles of any diameter. The scattering is sensitive to the particle size. The intensity of the scattered light is generally not strongly dependent on the wavelength. When all the wavelengths of white light are scattered equally, then Mie scattering is occurring. Mie scattering coincides with Rayleigh scattering in the special case where the diameter of the particles is much smaller than the wavelength of the light. Mie scattering intensity for larger particles is proportional to the square of the particle diameter. Sir C.V. Raman from Tiruchirappalli, Bangalore, India, was studying scattering of radiation. He won Nobel Prize in Physics in the year 1930 for his discovery of Raman effect. Raman scattering. When a beam of light with intensity I0 and frequency nu0 passes through a scattering medium, most of the light will be transmitted with intensity I and frequency nu0. But a small amount of radiation will be scattered in all directions. The scattered radiation found to contain nu0, nu0 minus delta V and nu0 plus delta V radiations. The total intensity of the scattered radiations will be about 0.1% of the intensity of the incident radiation. Raman scattering can be better understood by considering the energy level diagram and the energy transitions presented here. Absorption and scattered radiations are represented between the ground state and the virtual state energy levels. A molecule in the ground state absorbs energy h nu 0, goes to the virtual energy state and then comes back to the ground state by scattering the radiation with the same energy. Or a molecule presented in the first excited state of the ground state levels absorbs radiation with the energy h nu 0, goes to the excited state and then comes back to the ground state by scattering the radiation with the same energy. This type of scattering is called Rayleigh scattering. This scattering is elastic in nature. Instead, if a molecule goes to the virtual energy state by absorption of radiation with the energy h nu 0, then comes back to the ground state by scattering of the radiation with the energy h into nu 0 minus delta nu. This type of scattering is known as Stokes scattering. Or if a molecule goes to the virtual energy state by absorption of energy h nu 0, then comes back to the ground state by scattering of the radiation with the energy h into nu 0 plus delta nu. This type of scattering is known as anti-Stokes scattering. Stokes scattering together with the anti-Stokes scattering is known as Raman scattering. Raman scattering is inelastic in nature. Raman spectrum consists of Stokes line with the frequency nu 0 minus delta nu, Rayleigh line with the frequency nu 0, anti-Stokes line with the frequency nu 0 plus delta nu. Total intensity of all the scattered light will be nearly equal to 10 to the power minus 3 to 10 to the power minus 5 of the intensity of the incident radiation. Intensity of all the Raman scattered lines will be nearly equal to 10 to the power minus 7 of the intensity of the incident radiation. Raman effect is very weak. Raman scattering. The salient features of Raman spectrum. Raman scattering is very weak. with the intensity 10 to the power minus 7 of the incident radiation. Total intensity of the scattered light is of the order of 10 to the power minus 3 to 10 to the power minus 5 of the intensity of the incident radiation. The strongest scattering is Rayleigh scattering. Stokes lines have greater intensity and lower energy. Anti-Stokes lines have lower intensity and greater energy. Raman scattering or inelastic scattering. Information regarding the molecular energy levels can be obtained. Thank you.